Now we are going to discuss about cement hydration. Cement is the binder which binds the aggregates together. As we discussed before, cement can be hydraulic or non-hydraulic. Hydraulic cement react with water and it makes the concrete harden, but non-hydraulic cement react with carbon dioxide in air and it makes the concrete harden. There are special situations where we have to use non-hydraulic cement, like when we do construction in underwater. But in general constructions, we use the hydraulic cements. And in this topic, we are going to discuss about the reaction between cement and water. Now let's look at the chemical composition of Portland cement. Portland cement has four main chemical compounds: C3S, C2S, C3A, and C4AF. C3S stands for tricalcium silicate. C2S stands for dicalcium silicate, C3A stands for tricalcium aluminate, and C4AF stands for tricalcium aluminoferrite. In a cement, 45 to 60% is C3S, 15 to 30% is C2S, 6 to 12% is C3A, and 6 to 8% is C4AF. However, this is the usual range. In a cement, it can be different. Depending on the percentage of different compound that we have in a cement, the properties will be different. The way the cement react with water will be different. So the setting time will be different. The strength gain will be different. And also the heat generation will be different. So we will be looking at those in future slides. And also we can find the oxides in a cement. If we know the percentages of calcium oxide, silicon dioxide, and other oxides, we will be able to calculate the four main compounds in a cement. Now let's look at how to calculate the percentages of the four compounds in a cement. To find the percentages of the four main compounds, we use the Boic equation. You can see the four equations here. We can find the C3S using this equation. As you can see, if we know the percentages of the different oxides, you can just substitute those values here and you can find the C3S. Similarly, you can find the C2S using the second equation, but you need to remember here in the second equation, you have this part which is your C3S. So you need to first find the C3S percentage and substitute it in the second equation to find the C2S. And also you can find the C3A using the third equation, and also you can find C4AF using the fourth equation. You have some questions in the tutorial and you can try these questions by substituting the oxides values and check whether you get the right answers. Hydration is the chemical reaction between cement and water. That means the reaction between these four compounds with water. Here we are looking at two things: the heat generation and also the strength gain with time. These are the four primary chemical reactions during cement hydration. As you see here, C3S and C2S react with water and it makes calcium silicate hydrate. C3A react with water and it makes calcium aluminate hydrate. C4AF react with water and it makes calcium aluminoferrite hydrate, and C3A react with water and it makes monosulfoaluminate hydrate. Now let's look at these four reactions closely. Tricalcium silicate, which is C3S, rapidly react to release calcium ions, hydroxide ions, and a large amount of heat. This reaction slowly continues producing calcium and hydroxide ions until the system becomes saturated. Once this occurs, the calcium hydroxide starts to crystallize. Simultaneously, calcium silicate hydrate begins to form. Ions precipitate out of the solution, accelerating the reaction of tricalcium silicate to calcium and hydroxide ions. Dicalcium silicate, which is C2S, react with water in a similar manner compared to the tricalcium silicate, but much more slowly. The other major compounds of Portland cement, tricalcium aluminate, which is C3A, and tricalcium aluminoferrite, C4AF, also react with water. Their hydration chemistry is more complicated as they involve reaction with gypsum. The four main chemical compounds are responsible for different properties in cement, and we can regulate the amount during the production process. Now let's see the functions of four chemical compounds. C3S contributes to early strength gain. C2S contributes to late strength gain. And C3A is an undesirable compound since it makes hydrant cement paste easy to be attacked by sulfate, but it is facilitate the combination of lime and silica during the cement manufacturing. C4AF react with gypsum and it accelerates the hydration. As the four compounds are responsible for different functions, when we are selecting a cement for a particular application, we need to look at the percentages of the four compounds in the cement. For example, a cement with a high C3S is recommended for repairing a busy highway where we need to gain the strength quickly. For a sewage project, a cement with low C3A is recommended because otherwise the cement will react with sulfate. A cement with high C2S is recommended when we have to delay the setting, for example, when we do concreting in a hot weather. The strength development with time during the hydration process is very important. You can see the grain development in the left-hand side picture, and you can see how the compressive strength is developing with time in the right-hand side picture. As you can see, C3S is gaining a considerable amount of strength in 7 days, but the other three compounds are not. However, C2S is able to develop the same strength over the time, but the other two compounds, C3A and C4AF, is not contributing in gaining strength. Heat of hydration is an important phenomena that we have to look at because in some situations we have to control the heat production during the hydration process. In this table you can see the heat generation by the four main compounds in cement. C3S is producing 502 joules per gram, C2S is producing 260 joules per gram, C3A is producing 867 joules per gram, and C4AF is producing 419 joules per gram. When you look at the weight composition in the four compounds, we have 45 to 60% of C3S in a cement and 6 to 12% of C3A in a cement. The main two compounds contribute to heat generation are C3S and C3A, but when you look at the weight proportions, we mainly have C3S in a cement. So the heat production is mainly contributed by the C3S, but also C3A is contributing a high heat of generation. Now let's look at the effect of fineness on cement hydration rate. Particle size of cement is an important property that must be carefully controlled during the production. Since the hydration starts at the surface of cement particles, the finer the cement particles, the larger the surface area and the faster the hydration. Therefore, the fine material results in faster strength development and a greater initial heat of hydration. However, increasing the fineness beyond the requirement is increasing the cost of production and also can determine the quality of cement. With this topic, we are finishing the hydration part and we'll move to the next topic.